Power
Okay, so let's talk
series.
about power series. So remember that the goal is very simple. The goal is to approximate functions of any kind, of any type, with polynomials. So it's sometimes easy to get lost in all the details, but the goal is to approximate functions via polynomials. And you already know that this can be done because we know, like we talked about the last time, that the sum from n equals 0 to infinity of r to the n is equal to 1 over 1 minus r, as long as r is less than 1. So flipping that around, restating that, just rewriting that just in a different way, saying if f of x is 1 over 1 minus x, then that's equal to the sum from n equals 0 to infinity of x to the n, as long as the actual value of x is less than 1. Right. So this is the statement in terms of series that we already proved. And this is the statement in terms of, hey, here's a function. I can write this function as an infinite polynomial. Right? That's what you've written it as. You've written it as an infinite polynomial. In other words, 1 over 1 minus x is the same as x to the 0, that's 1, plus x to the first, plus x squared, plus x cubed, plus as long as absolute value of x is less than 1. So there's a little bit of language here. I mean, that's surprising, right? That's a rational function. It's surprising that you can write it like a polynomial, isn't it? Doesn't that seem just strange? That you're studying polynomials all your life. You're studying rational functions that are polynomials divided by polynomials. And here's one that you can rewrite completely as a polynomial. But you're going to be able to do that for sine and cosine and e to the x, any function. You're going to find we're going to create a systematic way to write it as a polynomial. Let me teach you just a little bit of the language. What if I stop to this? If I said, well, if I just cut it off at 1, this is a line, right? Now, so that's the best linear approximation to this function. If I've added an x squared, that would be the best best linear approximation. Best parabolic or quadratic.
Just choosing either the first two or the first three terms?
Right.
Essentially.
Yes, yeah. Pick the next fourth one. Best cubic approximation, right? Exactly. So this is, why don't we just start with just kind of talk about what the goal is. For each function, I can, because your calculator can't add up infinitely many numbers, right? So if you're going to approximate sine x, then you can do the best linear approximation to it, or the best parabolic approximation, or the best cubic approximation, or the best quartic approximation. However far you need to go to get a good approximation to the function. And there are two things to think about. If I tell you you're going to approximate sine x, which is one of your problems in the notes there, is to approximate sine x. What information have I left out if I say, give me the best linear approximation of this function? What have I not told you?
The actual function?
Not what I'm looking for. What have I not told you if I say, give me the best linear approximation of this function? At what point? That's exactly right, Corey. It's like if I told you to give me the tangent line to it. If I said, give me the tangent line to this function. There's infinitely many tangent lines to it. Which one do you want, right? Tell me which one. So when you're creating a Taylor polynomial or a power series, first there's a letter which for some reason we always call C, which tells me where do you want the approximations. So there is now that I've picked the C, Corey's told me I've got to pick a number, so I picked one over there. What's the best linear approximation? Well, there it is, right? That's definitely the best linear approximation of that function right there. That best linear approximation. But just like with this one, I don't have to stop with linear. I can find quadratic. There's a quadratic somewhere in here. I don't know exactly what it looks like, but it doesn't look like this, right? It looks something like this. That's quadratic. Now here's a question for you. Sometimes something weird happens. What do you think the best cubic, if I said let f of x be a plus bx plus cx squared plus dx cubed. Suppose I said I wanted the best cubic approximation here. Well,
It would conform to the sine more, wouldn't it? It would be more similar to the sine function, wouldn't it?
well, the idea is they should be better and better and better approximations, right? Sometimes it's the same as the parabola, because maybe the cubic, maybe I could get a cubic that would fit like this and fit it better. But notice that it only fits it better nearby, right? But I haven't done this one in a while, so I don't remember. Sometimes the best cubic approximation turns out to be the quadratic. In other words, the coefficient is 0. But you see, this parabola maybe fit it really, really well. So maybe adding another term, I can't actually fit it better than I fit it with a parabola. So every once in a while you're surprised. You figure the best cubic and it's like, wait a minute, that's the same as I got for the best quadratic. Okay, so now in your notes, I make you do this two different ways. I make you do it the long way of understanding, no surprise there, right? I make you do it the long way so you'll understand what they mean. And then there's a pattern for it. So what do I want to say? I want to say, one, the Taylor series or power series are always centered about a point. So let me give some concluding statements. One, what does a power series look like? The definition is it means the sum it always looks something like this. Now, coefficients, right? That's what we're going to try to find out. Point of interest. That is, where are we approximating our original function? And so there's three things that we want to know, and the last thing we're going to want to know is where or what numbers is our approximation valid. That's called two fancy words, radius of convergence or interval of convergence, and they really mean the exact same thing. Let's go back to our example over here to make that clear. We said this was equal to this only when the absolute value of x is less than 1, right? So 1 over 1 minus x, at 1 is undefined. For large values of x, it's negative. Looks like this. So, if the absolute value of x is less than 1, in this picture, what values of x am I allowed to consider? If the absolute value of x has to be less than 1 for this equal sign to hold, what values of x am I allowed to consider?
Higher than 1?
Not higher than 1.
I guess.
Because 2, the absolute value of 2 isn't less than 1, is it? Nope.
Everything between
Is
0
negative?
and 1.
Is the absolute value of negative 3 less than 1? No.
Everything between 0 and 1.
That's part of it.
Between -1 and
Between -1 and 1, right? Because if the absolute value of x is less than 1, this means the same thing as this, right? That's the definition of absolute value. It means that. What else to say? So that's what we call our interval. So for this guy, the interval of convergence for this, for 1 over 1 minus x, is -1 to 1. Now, what's the width? What's half the width of that? 1. That's the radius of convergence. So the radius of convergence, it says, how far can you go away from 0 in each direction and still have it converge? So, which is the same, so this is the same statement as radius of convergence is 1. So for our example over here, like if this is my cubic, it's pretty obvious that things are going horrible way out here, right? This approximation is terrible way out here. It's only good close by. So there's some interval of convergence. It says as long as x doesn't get too far away from c, I can approximate sine x at this point using this polynomial. So the good news is you can write every function as a polynomial, and the bad news is only for a very narrow range, only for a very small area away from where you are. And that every time you pick a different c, if you pick this for your c, well, that linear approximation isn't going to be any good, right? The linear approximation is going to look like that. So for every different number you pick, the linear approximation is different, the quadratic is different, the cubic's different, everything's different. So you have to do it again at every different point. It's not like there's one infinite polynomial that tells you what sine looks like everywhere. The story is, wherever you are, you tell me where you are, right here, I tell you the best linear, then I tell you the best quadratic, then I tell you the best cubic, but they're localized to where the point that you're at. Questions so far about my meanderings? Mm-hmm.
Is there ever going to be a point, like where there's a point picked where there's not a linear?
The question of which functions have taper series is an interesting one. But let's just say the following. If your function is differentiable, it has a derivative, then it's always got a tangent line. But if you create a function like this, there's not a tangent line, so I cannot approximate it at that point. I don't know what the best linear fit is, because that line and that line both fit it equally badly. right? But if you tell me it's nice and smooth everywhere, it's got a derivative everywhere, then I can always find you the best tangent. If a second derivative exists everywhere, I can find you the best quadratic. If the third derivative exists everywhere, I can find you the best cubic. But it depends on how many derivatives you've got. Now in calculus, you kind of get the misconception, because we don't spend hardly any time on messy functions. You kind of get the impression that every function has as many derivatives as you want. And that's not a true statement. Okay, let me, so I want to mention the interval of convergence.